Hello, this is Brian Washburn. I'm going to do two problems using Lagrangian mechanics. I know the title of this is two nasty problems, but that's more for show than anything else. Okay, so I'm going to do two reasonable, somewhat nasty problems using Lagrangian mechanics. And these are we did both of these problems in recitation, and I just want to do both of them here for you now. Okay, so the first problem I'm going to do is what I have a rod, and that rod is frictionless. I have a mass that's constrained to move along that rod, and that rod then rotates with an angular speed capital omega. And so what I want to do is basically come up with equations of motion. I want to see if there's any equilibrium positions, and if there is any equilibrium positions, I want to find the frequency of small oscillations. Okay. What we're going to find out is there will be an equilibrium position, but that equilibrium position will be an unstable equilibrium position. So there will be not any frequency of small oscillations. So that's what we're going to show. So what we're going to do is let's get the equations of motion first by writing down the Lagrangian. Now, before I write the Lagrangian, let's first write down the equations of constraint. And what I'm going to do is I'm just going to draw a picture. So I have this is my z-axis, and then let's just look at the yz plane here. This is z, this is y. And at some instant time, I have an angle here. And that angle there, I have an angle alpha here. Okay. So then that gives me an equation of constraint. One equation of constraint is going to be tangent of alpha is going to be equal to rho or z, where rho, and in this case, rho is going to be along the y-axis and z is perpendicular to that. So that's an equation of constraint. The other equation of constraint we have is that rho dot is equal to capital omega. Okay, those are my equations of constraint. So now what I'm going to do is using those equations of constraint, I'm going to write down the kinetic energy and potential energy. Obviously, a good coordinate system is going to be a cylindrical coordinate system. Okay, so the kinetic energy is 1/2 mv squared. V in a cylindrical coordinate system in general looks like rho dot rho hat plus rho v dot v hat plus z dot z hat. Okay. However, what we can do is we can relate. So z dot and rho dot are related by the equation of constraint. So I can say from the equation of constraint, I can say that z. So at this point, I can get rid of either rho or z. And what I'm going to do is I'm going to get rid of the variable z. You could get rid of rho if you want. Okay. Using this equation of constraint, I can show that, say that z is equal to rho times the cotangent, which is 1 over tangent of alpha. If I take the derivative of that, that means that z dot is equal to rho dot times the cotangent of alpha. Okay. And then from that expression, I can say that v in general, well, for our problem, is rho dot rho hat. Okay. Plus, and then rho, now instead of phi dot, using the second equation constraint, phi dot is equal to omega phi hat. And then here, instead of having z dot, I have rho dot cotangent alpha. Cotangent alpha is just some constant, and then that's in the z hat direction. Okay, so now I can calculate v squared just by taking the v dot v, rho dot squared plus rho squared omega squared plus rho dot squared times cotangent squared alpha. Okay, so that's v. And then the kinetic energy is just 1/2 mv squared. So then what I can do is notice that I have here a rho dot squared and a rho dot squared there. I can write that as rho dot squared 1 plus cotangent squared alpha, okay, plus rho squared delta squared. Now there is a trig ending which I could do. 1 plus cotangent squared is equal to cosecant squared. You all know that, right? Yeah, that's what I thought. So anyhow, what I can do is I can write this as 1/2 times rho dot cosecant squared alpha plus rho squared v dot, like that. Okay, so that's the kinetic energy. Potential energy, that's easy. U is just going to be equal to mgz. Okay, but I got rid of z, so that's just going to be mg rho cotangent of alpha. Okay, and then my Lagrangian is just going to be t minus u, and just write it out. So you can see minus u. Did I do that right? Yep. Okay, so you can see my Lagrangian there. First of all, it only has, it's a one-dimensional problem, okay? And the one-dimensional, 1 degree of freedom is rho, okay? And the reason why is because the equation is constrained. Z and rho are coupled, and then phi is constrained by the constant angular speed. So that is my Lagrangian. Okay, now what I'm going to do is I'm going to get the equation of motion. Again, this is one-dimensional, so let's use the Euler-Lagrange equation. Oops. Switch that over. Okay, so let's calculate. Now, if you take a look at the form of the Lagrangian, notice that there's a rho dot and a rho, so I would not expect any momentum associated with rho to be conserved. Okay, so I'm going to take a look at partial L respect to rho. Okay, so then I have a rho here and a rho there. So that's going to give me equal to m let's see. Yeah, m rho omega squared. Okay, that's from this term here. Okay. And then minus mg cotangent alpha. Okay. That's partial L respect to rho. Partial L respect to rho dot is equal to m rho dot cosecant squared alpha. Okay, and then I'm going to take the time derivative of that same thing, and that's going to give me m cosecant squared alpha rho double dot. Okay, so I'll stick that into the Euler-Lagrange equation, which is this. Rho. So then I'm going to get here m rho omega squared minus mg cotangent alpha minus m cosecant squared alpha rho double dot equals 0. I can divide. Okay, so I'm going to take this term here, put it on the other side, and divide by cosecant squared. If I do that, or mass times cosecant squared, I'm going to get rho double dot. And this is going to be equal to, now, so when I take 1 over cosecant squared is sine squared, so I'm going to get rho omega squared sine squared alpha. And then I'm going to get cotangent divided by cosecant squared. Playing with trigonometry, you can show that's just equal to sine times cosine. And so the masses cancel out, and I'm going to get minus g times sine alpha cosine alpha. Again, these are just constants. That's it. That's my equation of motion right there. Now notice it looks kind of complicated, but it's not really that complicated. It's just rho double dot equaling a constant times rho minus a constant. Okay. In fact, let's just write out the differential equation on one side. It basically says that rho double dot minus some constant times rho plus another constant equals 0. Okay. Now, you may look at that and say, well, is that really simple harmonic motion? No, because of that minus sign there. In fact, the solution to this differential equation is going to be a cosh or a sink. Okay, so this equation here is not simple harmonic motion. Now, one thing we can do is at this point, we can multiply mass times rho double dot, and this is going to give me m rho phi squared sine squared alpha minus mg sine alpha cosine alpha. Now, this thing here looks like of the form mass times acceleration, and then I'm going to define this as some effective force. So this quantity here is what I'm going to say is an effective force. Okay. Now when we look at that effective force, we can look at that thing and plot it and try to find equilibrium positions, okay, based on that effective force. Okay. Now what we're going to do is we're going to plot that, and then we're also going to look at equilibrium positions. Okay, so let's do that in the next slide. So what I'm going to do is I'm just going to, let's look at that in the next slide. Okay, so this is my equation of motion here, and then I'm going to call this quantity here an effective force. Let's first find equilibrium positions, okay, and then eventually we're going to find frequency of small oscillations, and then from plotting the effective potential associated with this effective force, I'm going to show that the equilibrium position is going to be unstable. All right. So let's first find equilibrium position. The way I find equilibrium position, I said rho equal to rho naught. Rho double dot is equal to 0. Put that into the upper equation, and I'm going to get 0 and divide by the mass is 0. Rho naught omega squared sine alpha squared minus mg sine alpha cosine alpha, dividing by sine, bringing one term on the other. I'm going to get g g cotangent alpha divided by omega squared. That is an equilibrium position. Okay. Now, let's show that it's going to be unstable, and I'm going to show it's going to be unstable by two ways. Let's first figure out the frequency of small oscillations. Okay. So what I'm going to do is to find the frequency of small oscillations, I'm going to set rho equal to rho naught plus delta. The rho double dot is going to be equal to delta double dot. Okay, stick that in the equation up above this equation here, and I'm going to divide by mass to do that first. So I'm going to get here where I do that. Delta double dot equals rho naught plus delta delta squared sine alpha squared minus g sine alpha cosine alpha. I'm going to bring everything on the other side. I'm going to get delta double dot minus g delta squared. So I'm going to basically multiply this term here. I'm going to look at the term times delta first. That's going to be omega squared sine squared alpha delta. Okay. Plus, and then I have a bunch of constant stuff. So the first constant stuff is going to be rho naught delta squared sine alpha squared minus g sine alpha cosine alpha equals 0. Now, this stuff here in that bracket is exactly, again, just the stuff that is here is exactly this stuff here, which is equal to 0. So then I can rewrite this equation as, that's funny. Let me delta double dot minus omega squared sine squared alpha times delta equals 0. Now that equation there, you might say, well, that's simple harmonic motion. No, it's not simple harmonic motion because of the minus sign. A solution to this equation is a, depending on initial conditions, a cosh or a sinh. Cosses and sinh are non-periodic functions. They exponentially go one direction or the other. So that is an equation at that equilibrium point is not simple harmonic motion. It's an unstable equilibrium point. Now, how else am I going to show that I have an unstable equilibrium point in a different way? Okay, and the way I'm going to do that is I'm going to plot the effective potential. So this quantity here, F effective, is equal to this stuff here. So let's plot the effective potential. Okay, so this is my effective potential. Okay, so now what I can do is I'm just going to define effective, this is my effective force. I'm just going to define an effective potential. So how do I get that? An effective potential is going to be equal to minus the work done by the effective force, which is this times the rho. If I do that integral, notice that here I have a constant. So that's integrating, that's going to give me minus 1/2. Minus comes from the minus sign at there. Let me write it out. So I'm going to basically do this integral here. Okay, so the first guy is going to give me minus 1/2 m omega squared sine, sorry, there should be squared there, rho squared minus sign. And then the other one is going to give me mg sine alpha cosine alpha rho. Okay, so let's plot that. So that's my expression. That's my U effective. So what I'm going to do is I'm going to plot each term individually. Let's plot this guy by hand, this guy by hand, and so let's do that. So here I have, oh, that wasn't very good. That's a little better. Okay, I'm going to have here rho and then U effective. Now let's look at the red term. The red term is a parabola, but with a negative number. So it looks like this. Like that. That's a parabola. That goes under the negative axis. Okay. The blue one is a straight line, and it does this. With a slope of mg sine alpha cosine alpha. And then basically what I have to do is, in the end, the parabola is going to win. So the function is going to do something like this and kind of come down like that. This point here is my equilibrium position. Now notice that is an unstable equilibrium point, okay? Because if I go off anywhere, the force will not be restoring force. So again, I showed that the equilibrium position is unstable by two ways. One, plotting the effective potential, and two, by looking at the frequency of small oscillations and show that I get a differential equation whose solution is a cosh or a sinh. Okay, so that's that problem there. I think the cool thing about this particular problem is we actually described a lot of physics without solving any differential equation whatsoever. Okay, so that last problem actually was the easier of the two problems. We're going to do another problem. I call this the Springy Pendulum problem. Somebody actually mentioned this problem in class. I said, oh, let's just do that problem. So what I have is I have a pendulum. Okay, I have a mass. Say that mass is attached to a spring, and then the mass can oscillate in this direction and rotate in this direction. And basically there's a restoring force due to the spring, gravity acts on the mass, or restoring force due to the spring, mass. And then one constraint we say the spring is always straight, so that the string doesn't bend, it doesn't curl, or anything weird like that. So what I want to do is I want to find equations of motion, and I want to get a differential equation. Okay, so let's do that. Okay, so again, you think about I have my springy pendulum, and so here's how did I do this? I have a x direction here, I have a y direction here, and then I have a spring, a mass, okay, like that. I'm going to call this angle here phi, and then the distance that it is away from the point here, I'm going to call that rho. All right. So obviously, using a cylindrical coordinate system is the best way to do this. And you might even guess there is probably two generalized coordinates. So there's really only one equation of constraint. The one equation of constraint is z must equal to 0. So again, there's one particle, 3 times one particle minus one equation constraint equals 2. I expect two generalized coordinates. Okay, and those generalized coordinates are going to be phi and rho. All right, let's write down the kinetic energy. Kinetic energy is equal to 1/2 mv squared. Well, in cylindrical coordinate system, v in just two dimensions using the equation constraint, v is going to be equal to rho dot rho hat plus rho phi dot phi hat, and dot is equal to 0 because z is equal to 0. So v squared is just equal to rho squared plus rho squared phi dot squared. So we've seen this multiple times, so that at this point we can almost just write down the kinetic energy because it's pretty straightforward. Okay, and then the potential energy. Well, then you have to define zero potential energy. Let's do it at that point there. And so then, so you got to be a little careful. There's two forms of potential energy. First of all, the total potential energy is equal to that of the spring, okay, and that of gravity, okay. I said zero gravitational potential at this y equals 0, x equals 0 point, okay, and then since the force was equal to minus k rho minus a. From what you know about potential energies, that the spring potential energy is just going to be equal to 1/2 k rho minus a quantity squared. Okay, that's the spring potential energy, and then the gravitational potential energy is just going to be equal to, well, it's going to be mgx. So this distance here is x, but x, we apologize for that, x is equal to rho times cosine of phi. Okay, so it's going to be mgx or rho cosine phi. So the total, so then the total potential energy is equal to, oh, by the way, so it's minus because it's under everything. And so it's going to be minus mg rho cosine phi plus 1/2 k rho minus a quantity squared. Okay, so that is kinetic potential energy. We write down Lagrangian. Lagrangian is 1/2 m rho squared plus rho dot squared. Forgot the dot. Minus u, but minus u is going to be equal to plus mg rho cosine phi minus 1/2 k rho minus a quantity squared. All right, that's my Lagrangian. Okay, so if you look at that guy, ask yourself, all right, is there a rho in there? Yes. Okay. Is there a rho dot? Yes. So the generalized momentum associated rho is not going to be conserved. Okay. Is there a phi in here? Yes. Is there a phi dot in here? Yes. That means that the angular momentum or the generalized momentum associated with phi is not going to be conserved. So there's no conserved quantities here. Well, except for mechanical energy, but there's no conserved angular momenta. Okay, so now what we're going to do is we're going to write down. Now we got two equations of motion because we got 2 degrees of freedom. So let's write down those equations of motion. Okay, so let's so we can either pick phi or rho. Let's pick phi for now. Sorry. So we're going to find the equation of motion for phi. Again, nothing is conserved. So I get 2 Euler-Lagrange equations. So partial L respect to phi is going to be equal to, so if you take a look at phi, there's one term that has a phi. So that's going to be equal to minus mg rho sine of phi. Minus sign comes from taking derivative of cosine. Partial L respect to phi dot. There's one phi dot. That's going to give me m rho squared. The 2's cancel out, phi dot. And then ddt of that same expression. Now you gotta be careful here. Okay, let's not do that there. Now this is where it's easy to make a mistake at this point. The reason why is because both phi and rho is time dependent, so you gotta be careful there. So what I'm gonna do is just write it out explicitly of this. Okay, I have to use a chain rule. So I'm going to take the derivative with respect to rho first. So that's going to give me 2m rho. 2 comes from the 2 there. Then I do the time derivative of that. So remember, I have to do a complete derivative, phi dot. Then I have to do plus m rho squared phi double dot. Okay? And you got to do that because both phi and rho are functions of time. Okay? Complete derivative, time derivative. Okay, so now we got everything. We can stick that into the Euler-Lagrange equation. I'm going to take this thing minus this thing here. That's going to give me minus mg rho sine of phi minus 2m rho phi dot rho dot minus m rho squared phi double dot equals 0. Now I'm going to group everything on the left hand side except for the minus mg sign. Now if I do that, let's take a look what I get. I'm going to get mass. So I'm going to take, so how am I going to do this? Actually, what I'm going to do is I'm going to take this expression here and this expression here, put it on the right hand side, and then flip the whole equation around. So what I'm going to get is I'm going to get m I made a mistake here. So, yeah, okay, so I made a mistake. No, that's okay. Hold on, let me check something here. Okay, I did not make a mistake. So what I'm going to do is I'm going to write m rho. I don't want that. Rho squared. M rho squared v double dot squared. And then I'm going to have everything else. I'm going to have, yeah, minus m rho sine phi. Okay. And then actually what I'm going to do, no, let's this, we'll just do it in steps here. And then here I'm going to have here minus 2m rho dot phi dot. Okay. So now what I'm going to do is I'm going to divide by rho, okay, on the side because there's a rho everywhere. Then I'm going to take this term here and bring it on the right-hand side and factor out an m. I'm going to get m times rho squared, just rho, because I divide by rho, phi double dot. Let's get rid of that. Okay, rho double dot. And then here I have plus 2 rho dot phi dot. That's from this guy here. And that's going to be equal to minus mg, the rho's gone. And I forgot the g here. There's a g there. Okay, that is my equation of motion. Now you may say, well, that looks complicated, but actually it is not. Okay. In fact, this is one problem where in some respects it looks complicated, but we could have used Newton's equations and got this from the start. You may say, why? Well, remember, A is equal to, and we derive this, rho double dot minus rho phi dot squared in the phi hat direction plus rho phi double dot plus 2 rho dot phi dot in the rho hat direction. Now notice that this guy here is the same thing as this. Now what is this? This, I would call this guy a tangential. Okay, so it's mass times a tangential. Then what is this thing here? Well, that is the tangential component. This is the tangential component of the net force. Okay, so that differential equation makes a heck of a lot of sense. Remember, if you think about my pendulum here, there are two forces acting on it. There is the spring force and there's mg. Okay, the spring force is completely radial. Okay, but there's a tangential component to mg. That tangential component is minus mg sine theta, or phi in this case. Sorry. Okay, so again, this was mentioned in class. One way of checking is make sure it gives us the same result as Newton's law. Now, it would have been hard to get Newton's law, but not that hard. Okay, so that makes a lot of sense. Okay, that's phi. Let's do rho. Okay, so now what we're going to do is we're going to get the equations of motion for rho. We got them for phi. Now let's do it from rho. All right. So what we're going to do is we're going to look at the partial L with respect to rho. Okay, that's going to be equal to, where's our rho? There's a rho here and rho there, so you got to do both of them. Mg, sorry, Mg cosine phi. So that's from this term, and then this term here, you get minus k. Oh boy, yeah. So I gotta be really careful here. So what I have, okay, hold on. Let's just go back. We got rows everywhere. Okay, so we have a row here, we have a row here, and we have a row there. Okay, so gotta be really careful. Okay, so then I'm going to get m. So I get here, I would get It's, it's 1/2 mass times 2 rho dot squared. Okay. Then here I get mg cosine phi, and then here I get minus k rho. Okay. Well, I'm going to get here, yes. I'm going to get that, actually, not just that. Okay. Okay. Now what I'm going to do is, so then I'm going to take partial L respect to rho dot. Fortunately, there's only one rho dot. That's m rho dot. And then take the time derivative of that. That's going to give me m rho double dot. Okay. All right. So that's cool. So now I'm going to use the Euler-Lagrange equation. Okay. And so then I'm going to say, this again, probably bored by now, so I have to write these things out so you remember what the heck we're even talking about. Does anybody ever make it this far in these videos? I don't know. But anyhow, here's what we got. So, oops, and the minus, sorry, there's a minus sign there. Oops, sorry. Okay, there's a minus sign there. Okay, so I'm going to do that. And that's going to give me here m rho phi dot squared plus mg cosine phi minus k rho minus a. Okay. And then minus m rho double dot equals 0. Okay. So now I'm going to rewrite the equation this way. I'm going to say rho double dot minus, and then here I have rho phi dot squared from that first term is equal to minus k rho minus alpha, and then here I have plus mg cosine phi. That's my equation of motion. Okay. Now, let's interpret what that is. All right. Now, before I do that, let me get a result from before. Okay. So, the result I had before was in this blue box. Now, notice that this is the expression for acceleration in the cylindrical coordinate system. And then, notice we used the tangential component, but there's also a radial component. Radial component is rho double dot minus rho phi dot squared. Well, that's what this thing is. So, I can rewrite this equation as mass times the radial component. This is the radial component of acceleration, which is the same thing as this, radial, along the radius rho hat. Okay, and then that's mass times the radial component. And what is it equal to? It's equal to the radial component of the net force. And there's two. So think about my pendulum, my springy pendulum. My springy pendulum has a spring, and then that. The forces that act on my springy pendulum are gravity, mg, and then a spring force. Well, obviously the spring force is radial. That's this thing here. And then a component of mg is radial. That's this thing here. Okay. So that's that equation right there. So again, we could have got that equation in Newton's laws. It would have been a little complicated, but in the end, we can use our understanding of Newton's laws to understand the result that we got from Lagrange mechanics. Now, if we actually had to solve this particular problem, we have to solve both of these equations simultaneously. All right. So what we would have there is we would have this equation here and this equation here. So in the end, we would have two coupled second-order differential equations. All right. Now, say I want to solve that using Runge-Kutta. what I would have to do is I would express the two coupled second order differential equations in terms of four. So remember, these are two coupled second order differential equations. In order to use Runge-Kutta to solve this, I have to solve this in terms of four coupled first order differential equations. Now, you can do that, and it's not that bad, but you can do it, okay? But so that's how you do if you needed to solve it. Obviously, these are very nonlinear equations. So, and then is there any frequency of small oscillations? Well, no. So this is what we got. All right, so that's two nasty problems there. These are problems I expect you to know how to do. So you should be able to do this stuff on the test, okay? We'll talk to you later. Bye-bye.